Okay, so yeah, let's pick up where we left this morning. So just to kind of back up here for a second and talk about where we're headed today and tomorrow. Um, Today we're going to continue to talk about chapter 2 and the solo model and build the basics. We'll see how far we get. Tomorrow, the agenda item will be that we're going to finish up chapter 2. And then also I have a reading from a book by uh, forgetting his first name, Easterly. Can't remember how in the world. William Easterly, thank you. William Easterly, that really has to deal with the solo model and why it's important. Okay, so anyway, that will be where we get tomorrow. So whatever we don't get in chapter 2 this afternoon, we'll finish that up tomorrow, and also talk about that Easterly reading. Okay, so those are the kind of where we're headed here over the next day or two. So this morning we left off, if you remember, talking about, well, does the solo model, how does it answer those questions about why rich countries are rich and why countries grow at different rates? Okay. And so we left off this morning with a strong prediction of the solo model that countries with lower population growth should be richer. And so let's make sure we understand why the solo model predicts that. And then we'll kind of talk a little bit about the implications. So let's think about an example here. We're going to draw our solo model diagram. Okay. Okay, so here we are. Here's our old steady state. And then let's work through the example of, let's say that there is a increase in population growth. So population begins to grow faster in a country. Well, in our diagram, what that does is that actually shifts this curve to be steeper. And as a result, we have a lower steady state. So in the short run, what happens? We actually have negative growth as we move gradually back to this slower steady state. So the level of capital actually shrinks, and as a result, growth actually shrinks. But it becomes less negative. I'm not sure if that's the way to say it. Less negative? Gets closer to zero. Maybe that's a better way of saying it. It gets closer to zero over time. And in the long run, growth goes back to zero. But the level of capital and the level of per capita output lower than before. So in other words, the country is richer, or I'm sorry, the country is poorer on a per capita basis. Now, I want to be clear about something here. When N bar goes up, L goes up and increases the level of output, right? So notice that the level of output goes up, and actually the growth rate of the level of output goes up. Because remember, what is the growth rate of output, the level of output? It's N bar. So when you have more population, the level of output growth actually goes up. But the problem is, Problem is that the per capita capital falls. And why is that? The answer, as always in this class, is diminishing marginal returns, right? Because of diminishing marginal returns, when you increase L, you do increase output, but not by as much to not reduce the average level of per capita output. Because diminishing marginal returns holds for capital and labor, right? So think of it this way, right? And this is, I think, a subtle point, but an important one. When you increase population growth, you increase the level of output. So in other words, the pie gets bigger. But what's the problem? You also have more people to cut more slices in the pie. And the problem is the pie doesn't get big enough so that everybody can keep the same size piece. Why is that? Diminishing marginal returns. As you get richer and richer and add more labor to a fixed amount of capital, the productivity of that capital is going to go down and you get a smaller increase in output than you need to increase to keep the per capita level of output high. So, in one sense, yes, more people means more growth, but it doesn't mean more per capita growth. And that's what we're really interested in if we're interested in thinking about standards of living. Now, this idea here in the Solon model actually is an idea that has a long history in economics, often referred to as Malthusian economics. Hopefully, many of you are somewhat familiar with Malthus or have heard his name, or at least have a little bit of idea of what Malthus was talking about. But Malthus wrote in the 1780s. Malthus was actually a minister who got interested in economics and became interested in demographics, and is often referred to as the father of modern demographics. And so he wrote a book called An Essay on the Principle of Population. And basically, Malthus saw three things. He observed population growth. So he actually went around and looked at birth records and saw very clearly that in England, where he lived, population was growing. The problem was he also saw that the capital stock was largely fixed. Thus, what was going to happen to per capita over time? Per capita capital. Per capita capital over time was going to go down, and per capita output was going to go down. And this would continue until you saw massive starvation. Of course, what's the nice thing about starvation, according to Malthus? The nice thing about starvation is it would actually increase your capital to labor ratio and would increase per capita output. But then people would have more babies, and you'd repeat the cycle. So Malthus really saw the future as one in which people were trapped in subsistence level incomes. That, yes, maybe for a period of time, society could rise above subsistence, but the problem is that when people have too much money, they have too many babies. And that was the trap that kept people poor. And so, Malthus obviously was a big believer in population control policies. And, this idea of controlling the population as being the way to become rich is actually an idea that has received a lot of attention over the years. All the way to consider the Chinese one-child policy, right? Was essentially a Malthusian solution to economic growth. How do we grow faster? We reduce the population growth, right? Is there evidence that the world is really Malthusian? Well, not really. So first off, let me explain what I mean by not really. Just going to show you, here's a picture that's looking at GDP per worker and population growth rates. So we see here on the horizontal axis, population growth, N bar, and on the vertical axis, basically per capita income. What do we see? Well, there is some evidence here that countries with higher population growth rates are poor, and countries with lower population growth rates are rich. So yeah, that you might say, well, that's Malthus, right? That's Malthus. That's true. However, as we're going to talk about a little bit later in the class, there is good reason to think that it's not population growth that is causing countries to be rich, but in fact, the causation works the reverse way. When you're rich, you have lower population growth. And when you're poor, you have higher population growth, right? So in other words, Malthus might be right about the correlation, but I think there's a lot of evidence to suggest that he's wrong about the causation. And so we'll come back and talk about this, but this is actually an area where I do not think that the Solow model is on particularly strong ground. The Solow model has this very strong Malthusian prediction, but I think when we come back, as I said, a little bit later in the class and talk more about the role of population in growth, we'll see that it's not nearly as simple as Malthus thinks, right? And that there's a lot of reason to think that how do you reduce population growth? You get rich, right? The getting rich is the way that you reduce population growth, not you don't reduce population growth to get rich, right? And so we'll talk about that a little bit later in the class. When we think here about Malthus, though, you really see what this Solow model is missing. Because when we go back to thinking about Malthus, I say here that Malthus saw two things. He saw population growth, and he saw that the capital stock was fixed. Why? Because in 1780, Britain was still largely an agrarian society. And so what was the biggest form of capital? It was still largely land, right? And so Malthus saw a couple things, but there's something that he did not see. And that is technology and innovation, and the fact that economic production could change dramatically. In other words, Malthus ignored technology. He did not anticipate the fact that we could move to a world in which land is not the primary stock of capital. Now, think about this Solow model that we've talked about. The Solow model that we've talked about so far there is no long-run growth. There is no way to grow in the long run. In the long run, you always get to the steady state. Why? Diminishing margin returns. You always hit that point of diminishing margin returns in which growth goes to zero. Why do you get that in this model, in this simple model that we've talked about? Because this simple model is a Malthusian model in the sense that it also ignores what Malthus ignored. It ignores technology. Technology and productivity. That there are ways to increase output other than getting more capital and more labor. So when I use the words productivity here, we're really talking about ways in which you can increase output with the same amount of capital and labor. A more formal definition is productivity is output per worker hour. So if I can get more output per worker per capital hour, I can increase my productivity. And so that's what's really missing from the solo model that we talked about this morning, is that there's really no other way to increase output but to increase inputs. And what's the problem with inputs? Inputs are subject to diminishing margin returns. But productivity has no formal limits. In other words, productivity offers us an unlimited scope of increasing output without the same physical limitations. So as we go on in this class, I'm obviously going to have a lot more to say about technology and where it comes from. In fact, that becomes a big part of our discussion on Thursday and Friday, and even on Monday in this class. So really, a lot of our toward the end of the week, we're going to come back and talk a lot more in detail about productivity and about technology. But for right now, we really have to just think, well, how can we add this to our solo model, right? What can we do to make sure that solo incorporates this aspect of production that we know is important? So let's think about this. How can we add technology in the solo model? Well, we're going to define a new variable. You can call this assumption number 9. A bar. Exogenous technology. Now, we are going to add technology in the solo model without necessarily explaining where it comes from. Okay? So we're going to make technology exogenous. We're going to allow for the possibility of technology to occur without really explaining where it comes from. Okay? So we're going to let A bar be the exogenous technology. And let's assume that A bar grows according to an exponential growth. It grows according to the following exponential growth formula. A bar 0, meaning our initial level of technology, e to the g times t power. So in other words, in this model, how fast does A grow every period? By the rate of g, right? So g is the rate of technology growth. And it is exogenous again. So we're allowing for the possibility of technology here without saying where it comes from, right? You can think about technology, for those of you who are familiar with the Bible, as manna from heaven, right? Manna from heaven is just basically food falling out of the sky. So here every day people wake up and whoop, here comes some technology down on us. Awesome. Now we have this technology. Now we can use it. So now with technology, our production function becomes this. Okay. We're going to make our production function this, right? So here, A bar impacts the productivity of labor. So when we have more A bar, it essentially makes labor more productive. What does this production function look like in per capita terms? It really looks just like it does before, but just one difference. We have A bar to the 1 minus alpha power, because that's what we're really adding to the model, right? We're just adding this constant, A bar to the 1 minus alpha power. So it looks pretty much the same as it did before. What if we express this in terms of growth rates? So we take logs of this equation and we differentiate with respect to time. I won't go through all the details. I'll just jump to the conclusion. What do we get? The growth rate of per capita output is going to be related to the growth rate of per capita capital and the growth rate of G. Now let's just use our intuition here before actually doing too much math. Let's see if we can just kind of figure out this equation and the implications of this equation through using our intuition. What's going to be true in the long run? In the long run, it's going to have to be true that whatever our growth rate is, it's going to be constant. In the long run, we have to have a constant growth rate. In other words, we have to have what's called a balanced growth path. It cannot be a long-run equilibrium for growth to be high one period and low next period. Whatever growth is going to be in the long run, it has to be constant. For growth to be constant, it's going to have to be the case that per capita output is going to grow at the same rate as per capita capital. Well, wait a second. If this is true here, what happens if we just plug this in up here? We solve that, what do we get? what's going to be true about the growth rate of per capita output in the long run? It's going to grow at the rate of G. And likewise, per capita output will grow. I'm sorry, per capita capital will grow at the rate of G. This is our balanced growth path. So before, we had a steady state. Where output and capital grew at 0 in the long run. Now we have a balanced growth path. Where these things grow at the rate of technology. Let's pause here for a moment and just make sure that we understand what's going on. Why isn't growth 0 in the long run? Does this model not have diminishing margin returns anymore? Well, it does have diminishing margin returns. But the key is technology is the way that we overcome diminishing margin returns. So the way we grow in the long run is technology, right? Technology allows us to overcome diminishing margin returns. And when we overcome diminishing margin returns, that's how we get long run growth. That's the intuition that we have now in our Solow model, now that we've added technology. Okay. Now, let's think about that Solow diagram with technology. Okay, this is a little bit more complicated. In fact, so complicated that I'm just going to warn you that you're going to have to put on your thinking caps here to kind of figure out what's going on, because this is a little tricky. How do we have a Solow diagram now that we have technology, right? Because notice now, we don't have a long run equilibrium. We have a balanced growth path. How exactly do we capture a balanced growth path on a graph? Well, to do this, we need to find variables that are stationary. And by stationary, we mean what variables are constant in the long run. What are these variables going to be? Well, let's define a variable that's called capital to effective labor. And we're going to call this K tilde. And what is K tilde? It's not K divided by L, it's K divided by A times L. And let's also define a new variable as output to effective labor, where the tilde once again means we're dividing by A times L. When you do this, you can rewrite the production function like this. So when we rewrite the model in terms of effective labor, why are we doing this? Because these variables are going to be stationary in the long run. Okay, these variables are going to be stationary in the long run, meaning these variables are not going to change in the long run. Okay. Let's come back to this for a second. Okay, we know that K tilde is equal to big K divided by A times L. If we put this in terms of growth rates, meaning we take the logs and we differentiate using that trick, we can rewrite the growth in K tilde is equal to the growth in capital minus the growth in A minus the growth in L. Or that. Okay? And now I just have worked it onto the left side. Plug this into our capital evolution equation. Which, remember, what's our capital evolution equation? It's this. Right? So plug this into there. And what do we get? We get this. Or we could also rewrite it like this. So to get this equation, I did the same thing I did this morning. Now we're just defining these new variables, K tilde and Y tilde, which is not just dividing by L, but dividing by A times L. How does this look different than this morning? Well, what looks different is we have these tildes here, right? But more importantly, notice what shows up. G. G shows up. Why does G show up? An increase in G bar actually reduces K tilde in this equation, which seems counterintuitive. But remember, what's K tilde? Right? An increase in G increases A and reduces K tilde. But do we care about K tilde? Not really. We care about per capita output. Okay? So while this looks unusual to think that an increase in G actually reduces K tilde, remember, we don't care about K tilde. We really care about little k, per capita capital. That's what we care about. So now if we look at our solo diagram, what does it look like? It looks like this, where we've designed the model in terms of K tilde. In the long run, K tilde star is the balanced growth path. In other words, what's true about K tilde, the growth of K tilde, and the growth of Y tilde? It's equal to 0. But big but, okay? But if K tilde is growing at 0, what's K dot? What's little k and little y growing at? G. So along the balanced growth path, Y tilde and K tilde are stationary, but little y and little k are growing at the rate of G. That makes sense? And to take it even deeper, okay, somebody gets brownie points for this one. What rate is the level of capital and the level of output growing at? Remember, this is per capita. So if per capita output is growing at the rate of G, what's the level of output going to grow at in the long run? Anybody? No brownie points? N plus G, right? So if per capita output is growing at G, the level of output has to be growing at the level of G plus the level of population growth to keep per capita output steady. Okay, so K tilde grows at grows at 0 along our balanced growth path, but K, little k, and little y grow at G. And the level of k and the level of y grow at N plus G. Okay, that can be confusing. No doubt about this, because it is confusing to have K tilde, little k, big K, right? And the same for Y. There's a lot of variables bopping around here. And yes, right, it takes a little bit of time to sink in, right? So I highly encourage you tonight, and we're gonna work through this model here for a few minutes and make sure that we kind of understand the mechanics. But as I said this morning, understanding the solo model cold is crucial to going forward. And so I really encourage you tonight that one of the things you really should do is go back and look through your notes from today, and particularly look through this first 40 minutes or so of our lecture, because I think this is often something that gets very confusing, right? Once you add technology to the model, it's almost like adding a third dimension, right? Now we have this third dimension that we have to think about in our model, and trying to keep all the notation straight can get confusing, right? Absolutely can get confusing. And And also, this is the way to talk about the solo model that we did not talk about in intermediate macro. So I know that those of you who took intermediate macro from me, we talk about the solo model, but we never really quite talked about it in this way. And so, yeah, this is a confusing bit of material. And so I really encourage you to go back, take a look at your notes, particularly this part of the notes. I'll send you some links to the lecture. If you need to go back and spend a little bit of time in the lecture, if there's something that you miss, you know, this would be good. It'd be good to do it tonight too, because as I said, because we're using the solo model so much over the next couple of days, the sooner you can get this kind of straight in your head, I think the sooner you'll really begin to pick up on the, you know, the really important details of the solo model. Let's do an example here. Let's think about our same solo model here, but now the model with technology, and let's think about how S increases when we have an increase in the savings rate. So once again, we're using the solo model with technology. And we have a balanced growth path. And I want to add a couple of other graphs here and think what's going on. Let's think about a graph about what's happening to the growth rate of output over time. And I want to add another graph where I look at the log of the growth rate of output. Okay? So by putting log here, this is a ratio scale. Okay? I'm putting this on a ratio scale. Okay? So as long as we're in the balanced growth path, what do these graphs look like? When we're along the balanced growth path, what's the rate of output growth? G bar. Output is just growing at G bar. And what's happening to the log of output? In other words, the level of output is just going up in a straight line. Right? It's just going up in a straight line. Then we have this change. It's at this date that there's the increase in S bar. Let's first go up here to our solo diagram. What happens in our diagram? When S bar goes up, this shifts up. And notice we move to a new higher balanced growth path. So we are going to begin to transition over time to this higher balanced growth path. What's that going to mean for output? In the short run, are we going to grow faster than G or slower than G? Faster than G, right? Because we need to get up to that new balanced growth path. Basically, what happens is growth immediately jumps way up, and then over time, it goes back to G. So we grow faster in the short run, and then we grow at G in the long run again. So this increase in S makes us richer in the short, or makes us grow faster in the short run, but doesn't affect how fast we grow in the long run, because in the long run, we always grow at G. What about the level of output? Hmm. Well, first off, we know in the long run it's going to have this same slope. But in the short run, we grow faster. So the slope has to go up. So in other words, what this is going to look like is growth goes up quite dramatically. And then over the long run, I didn't really draw that particularly well, but you see it goes back to the same slope that it had before. So we get richer in the long run and we grow faster in the short run. That's what happens here. So the amazing thing is, maybe it's not so amazing, but the thing is, this model, don't make this bigger than it has to be. In many ways, this is the same model that we had before. What's the key difference? Before, growth always went back to 0. Now, growth always goes back to G, right? So in other words, we always go back to a constant. It's just the question of what that constant is. In the model this morning, without technology, that constant was 0 growth. Now we go back to a positive rate of growth. And what's that positive rate of growth? The growth rate of technology, right? The growth rate of technology. So in the long run, how fast you grow depends upon what G is. In the short run, how fast you grow really kind of depends upon how far away you are from your balanced growth path. And so that's actually, I think, a good next thing. Let's use this model how does this solo model with technology answer our 3 big questions? Why are rich countries rich? This model has a pretty clear prediction. Rich countries are going to be rich if they have a high savings rate, if they have low population, but very importantly, this is the new part, a high rate of technology growth. Right? In fact, you can show, I'm not going to work through this algebra. You can actually do this yourself. It's pretty easy to do. But if you look at the balanced growth path level of output, it can actually be solved like this. And so you can very clearly see here that an increase in S increases Y. And a low N increases Y. G is a little bit more complicated, right? A high G, because it's in the denominator here, actually seems like it could reduce Y. But remember, when G goes up, what also goes up? A. And A here has a much bigger proportional effect than this G down here. because we have this to the alpha divided by 1 minus alpha exponent. So in other words, yeah, right, you can see this in the algebra too. But I think our intuition should tell us the same thing, that what makes a country rich, at least in this Solow model with technology, high S, high N, high G. I'm sorry, I said that wrong. High S, low N, high G. So that's the strong prediction of this Solow model, right? That's the strong prediction of the Solow model. Our second big question. Why does growth differ across countries? Well, here I think the answer is a little bit more subtle because there's really an answer for the long run and there's an answer for the short run. In the long run, why does growth differ across countries? Because different countries could have different levels of technology growth. Countries that have more technology growth grow faster. Countries that have lower technology growth grow slower. What does this Solow model have to say about why different countries would have different technology growth rates? Nothing. Right? This model says nothing about why G might be different across countries. So, some countries are lucky and more technology falls from the sky, and other countries are unlucky and they don't have it fall from the sky. That's it, right? It's completely exogenous. So this model doesn't tell us where G comes from, but G could be a source of differences in growth rates in the long run. In the short run, there's another factor. How far a country is from its balanced growth path. A country that's below its balanced growth path will grow faster than G. And if it's above the balanced growth path, it will grow slower than G. Why? Whenever I ask why, diminishing marginal returns. There's a pretty decent answer, the chance that that's going to be the answer. So here we have kind of a long run reason why growth differs across countries and a short run reason why growth differs across countries. So just as an aside here, I think this is just an absolutely crucial assumption to understanding how the world works, is to understand that there's different reasons why different countries grow, right? That sometimes countries are growing because they're on their balanced growth path, and sometimes countries are growing because they're not on their balanced growth path. So just to pick an article here that I pulled out of The Economist, it kind of illustrates this. There we go. Okay, here's an article from The Economist that actually kind of summarizes some recent research. And it says growth tends to slow when GDP per head reaches a certain threshold. China is getting close. Why does growth slow when GDP per head reaches a certain threshold? Diminishing marginal returns, right? Diminishing marginal returns kicks in more strongly as you get richer. And the point that this article's to make is if you look across countries, it's pretty clear roughly where that point is. And it is roughly, according to this article by Barry Eichengreen and among others, that level is about $16,000 per person, per capita GDP of about $16,000 per person. And so you can see here for these different countries how fast they grew before hitting this threshold and how fast they grew after hitting this threshold. And most of these countries, the US and Great Britain are actually somewhat outliers here. But for Australia, Japan, Hong Kong, South Korea, there was a pretty big slowdown that occurred after hitting that threshold. Of course, where is China's per capita GDP? Pretty much at this threshold, right? I mean, it depends upon exactly how you measure purchasing power parity, but China is essentially right there. And lo and behold, what's been true about Chinese growth the last 3 years relative to the previous 17? It's slowed fairly dramatically. And that was predictable. And not only was it predictable, but I have to say it's so frustrating when people don't understand, some basic ideas in economics. Not only is it predictable, but I've heard some people say, oh, well, China, they're falling apart and, things are collapsing. Now, listen, there are lots of reasons to be worried about Chinese growth in the long run, and we'll talk about some of them. But the fact that growth is slowing in China is actually the symptom of success, not failure, right? It's a symptom of success. You want to be a country that grows slow because you're rich, right? China is slowing in growth largely, I shouldn't say largely, but for a large part because they have gotten richer. That's a good thing. You would prefer to be rich and growing slow than poor and growing fast, okay? So this isn't, the fact that countries slow down is no way, shape, or form an indictment of that country's economy. That is actually the positive symptom of having faster growth. And the Solow model predicts that very well, right? It says, yes, eventually every country is going to slow down to the rate of their technology growth. That, I think, is where there might be a little bit more skepticism about China, right? What's the long run rate of technology growth in China? We'll kind of talk about this, I think, a little bit later in the class. But, the fact that China is getting closer to growing at its rate of technology growth is really a good thing for China, right? Because it means that they've gotten richer, right? And that's where you want to be in the long run, right? You want to be rich and growing slower, not poor and growing faster. All right, very briefly here, because we're running to our limit of an hour. The third big question is, how do you explain growth miracles? Well, I think that's pretty obvious here. It's got to happen because there's been something that has changed S, changed G, changed N. The problem is that in the Solow model, these are completely exogenous. We're going to have to move beyond the Solow model if we want to think about why savings rates or why technology growth or why population changes. But if you think about what a growth miracle is, a growth miracle is when a country sees an increase in their savings rate, an increase in G, and maybe a decline in population. What happens? You start to grow and you're far below your balanced growth path, so you grow fast. That's basically a growth miracle. So basically, you have a big increase in your balanced growth path, and you take off. right? And you grow faster than the rate of G. And so how, for instance, how did China sustain on average an 8% growth rate for nearly 30 years? You know, the simple answer is in part because China was such an economic disaster for the previous 600. I mean, China in many ways was an economic disaster. And so when things happened in their economy, we'll kind of talk about this, but there were exogenous changes in S and G and N. All of these things greatly increased the balanced growth path of China and led to a remarkable takeoff, right? But as we said, over time, China will slow down. That's predictable because the growth rate is not going to grow greater than G forever. Eventually, you're going to slow down to your rate of G, your rate of technology. And that's a symptom of success, not a symptom of failure. Okay, that seems like plenty for today, right? That seems like plenty for today. So we actually got through a really big chunk of chapter 2. And so there's just a couple of things related to convergence that I want to talk about tomorrow. Also, I think tomorrow I'll probably begin by just going back and making sure that we completely understand this solo model with technology. So, so make sure you look through all of your notes from today, but particularly maybe the notes you took this afternoon, and make sure you understand this solo model with technology. I'm happy to spend some time first thing in the morning reviewing this. I might go through a lot of this again just to make sure that we really kind of get it, or at least go through a couple of examples of doing this so that we make sure we understand this. Then we'll talk about convergence, and then we'll also talk about the reading from chapter 2 of Easterly. Okay? All right, folks. Thanks for your attention and hard work today. We will see you at 9 a.m. tomorrow morning, okay? Okay, have a good one.